computational graph. So we will see that so you saw in college that we can take derivative of many different functions. And now we will try to do it on a program. And it's not something that is trivial to do. So here I will have one variable x, and I will give it to f. It will produce me a variable y that will be given to g, and g will generate z. So as a program, I can program this as a Python code. So f of x here will do something with x, return y. G will take y, do something with this, and return z. And mathematically, I have these two equations. Here I have only a representation. It's not related to deep learning. It's only to see variables as nodes and function as the edges. And now, if I move a little bit x, how z will change? So I can compute the result just by comparing the two values, or I can use the derivative of the function f and g that we have just seen. So if I move a little bit x, to compute how y will change, I will use my linear approximation. So I will compute the derivative of f evaluated at x times the little modification I'm doing to x, so time delta x. And again, to compute how z will change, it's the derivative of the function j evaluated at f of x times the delta y. And since I'm only controlling x, and I want to see the impact, I will replace delta y by its definition here. And now I have this expression that will give me how z will change locally if I'm not changing delta x too much. So what information do I need? I need to know the definition of g. I must be able to find the derivative of it. I must be able to evaluate the derivative at a given point here, where the graph was evaluated first. So it doesn't make any sense to do a modification of delta x if I don't know where am I on the x-axis. I must be at a given point at x, and then I can study how z will change if I'm doing a modification over x. So let's see another computational graph, a little bit more complex. Here I will have one function associated to one node, so fi for f1 for y1, f2 for y2, etc. And then I would have one function gi for one node, and here the result will all be combined to give the value of z here. So I'm summing over the gi. How can I compute how z will change if I modify the input? So here it's only, we know from our courses in college that the derivative of a sum is the sum of the derivative inside the sum. So I obtain this formula here, which is different. Here it's only the definition applied to each function individually. And now I replace this delta yi that I've defined here. I obtain this function. And now I will do one more step just to show you how complex this thing can become only for a very simple graph. So here I have one function that will map one input to one output here, the f j to y, to I. And so I have my variables yi that will be defined as the sum over all incoming values of my function here. And the gi will be evaluated at these yi, and I sum to obtain the final value of z. And here I will be interested to, at a given point, so the point here now is a m-dimensional space. I'm at this point in space, and then I can move any of the variables with delta hi, and I will see how z will change. So again, my formulas of the chain rule, I defined, so this is only yi. And now here I have my delta yi, so I can replace this term by this expression. And I obtain this monster, and we will stop here after that. But it's only to show you that here I can do some simple algebraic manipulation, and I can convert the modification of z into a scalar product. So again, I have clearly separated the delta h, how I can move each of these variables as the input. And here I have this nabla z, which is the gradient. And how is it defined? It's defined by this expression. And in fact, to know the impact on z when I do a modification on h, I only need to compute this quantity, which is the gradient.